Hey guys, hope you're doing well. I still have a cough, for which I apologize. Hopefully it won't get in the way. I'm actually doing confidence intervals and recording this, so you may have seen this before. It's a new version. It should be better. My voice isn't better, but I have a new pad, new tablet, so that should be fun. Let me move some stuff out of the way. I only have 15 minutes, right? So I'm going to try to make this pretty quick, but I'll let you guys know what's up. So, confidence intervals. What haven't I told you yet? Well, let's assume that I haven't told you anything. We've done sampling distributions. This is where we start adding value. This is, okay, my handwriting will get better, I promise. The beginning of inferential statistics. What that means is we're beginning to add value. We're beginning to say things about the way the world works outside of just our lab or whatever, wherever we get our data. Okay, so the beginning of inferential statistics. And what we've done so far is we've assumed we knew a lot of stuff, but now we're not going to assume we know so much. In particular, we will admit that we don't know the mean of the population. That's the population mean. For now, we're still going to assume that we know the population standard deviation, which is sigma x. I assume we still know that. We're going to make guesses about the true value of the population mean. That's what we're going to do. So, what we know is that if we take a sample of, say, any size n greater than or equal to 30, we can just pick one for now. We'll use n as 50, say. If we draw a sample, and then we take a sample mean, that sample mean is going to follow a distribution that looks something like this. That's supposed to be bell curve. It's close enough. We have x bar. It's like we're drawing from a distribution with this shape. The mean is at mu sub x. The standard deviation of the sampling distribution is equal to sigma x over the square root of n. It's normally distributed. That's the mean. That's the standard deviation. This is a concept or an abstract idea, though. We can't really see this. In practice, when we draw a sample, we're going to get a sample mean, and it might be this one, right? Maybe this is our sample, x bar 1, right? Or maybe it's here, x bar 2. Or maybe we draw one that's all the way over here. Maybe we end up getting a really weird sample that's all the way down here, x bar 4. But chances are, what's going to happen is we're going to get our sample mean is going to be somewhere in the middle, probably, right? Occasionally we'll get one that's cut out here or out here, but very rarely, if ever, are we going to get one that's all the way out on the tails. We know that that's the distribution. The problem is that we don't know where this distribution is located. We know what it's shaped like, because we're still assuming that we know the standard deviation of the population. We don't know where it's located. Okay, so what that means is that when we actually take a sample and we make a guess at what we think the sample looks like, our best guess is like this. Let's say we drew a sample. We've got a sample mean. And our best guess, let's say this is our sample mean. Our best guess for what the actual sampling distribution is something that looks like this, right? Because that's our best guess for our population mean. X bar equals question mark mu x. That's our best guess. We don't know what it actually is. But if we had to put a number on it, that's what we would choose. The truth is that we don't know what it is. Let's say we still know this. We don't know what the true value of the population mean is, and we know that we are almost certainly wrong, right? The probability of being right is very small. We'd have to be drawing a sample mean that's right on this line right here. That's probably not the case. Now, what that means is that it could be that this is the true sampling distribution. It's got the same shape, but it's located differently. It could be that it's over here, right, just slightly to the left. Where am I? Right here. It could be that it's just slightly to the left. Right? It could be any of those curves. Right? What we're trying to do is, and for each of those cases, what that would mean is that the true value of the population mean is the middle of that distribution, right? The true value for the green curve is I can't see my pen. Where's my pen? Oh, it's up there. Okay. The true value of mu x might be here, right? If the green curve is the true one, and our x bar just happened to be on the high end. If our x bar happened to be on the low end, right, like in this red distribution, our x bar is in the low end, then the true value of x would be here. So we know that we're wrong. Our best guess is mu x. But based on the fact that we know something about the sampling distribution, we can make some inferences about what the true value is likely to be. So let me get us some more pages here. What we can say is, okay, well, I'm going to draw a sample. I'm going to select a sample. I'm going to get an x bar. Right. Now, there are two major cases, right? Well, there's three cases. This never happens. Case one, our x bar is exactly right, and that's mu x equals x bar. That's probably not the case. Then there's also the possibility that our x bar is weirdly high, right? There's an outside chance that it's weirdly high. We happen to get a really unlikely sample. And that's case one. And case two is, well, our x bar is weirdly low. What do these look like in practice? Well, we can take a look. Now, what this would look like, say we selected a sample, got an x bar, and our x bar was here. Okay. Now, it would be really nice if that were the population mean, but we can at least put some bounds on how wrong we are. If our x bar was weirdly high, what that means is that it was in the upper tail of the distribution. So the true distribution would look something like this. Right? And we chose an x bar, which was right here. And the true value of mu, the true population mean, is actually over here. Now, if we chose the case where our x bar is weirdly low, what that means is that the true distribution looks something like this, where this is the true population mean, and our x bar was in the left tail. Okay. What that says is that we know that mu is probably not going to be over here, right? Because that would mean that our x bar was really in the tail. It would have to look, it would have to be all the way in the tail. That would mean we got a really rare sample. And we know that our mu is probably not over here, because that would give us another really weird tail, right? We'd have to be all the way over there. Which means that the purple one and the red one, whatever the x bar is weirdly low, x bar is weirdly high cases, right? Those are our bounds. Anything other than that is just plain unreasonable. And that's what a confidence interval is, right? So what we can say is the true population mean falls somewhere in here with a certain percent level of confidence. So once we define what weird is, right, say 95%, right, or 5% outliers, then we can say, well, if our x bar is not weird, and we're assuming that it's not, right? If our x bar is within the normal 95%, the reasonable 95%, then the lowest our population mean could be is mu1, and the highest our population mean could be is mu2, and that's what a confidence interval is and does. All right, so see, I used up 8 minutes of our time. I can say one more thing about this before we go to a practice problem to show you what that looks like. If we increase our sample size, what that does, increasing our sample size means that it tightens our distribution, which means the definition of weird changes. Now we might have tighter distributions, which would mean that would be, this mu would give me a weird value of x. X bar would give me an x bar that was weirdly high. And a sample population mean that's over here would give me a weird value of mu2, which means that our confidence intervals shrink as our sample size increases, if that makes sense. Because you'll see as we go through a practice problem, the tighter the distribution, the smaller the margin of error. Okay, so let's say we have number of miles driven by the renter of a rental car. That's the example I've given already. You may have worked through this already. Just want to walk through it one more time. Take a sample of 200 people, n equals 200. They all drive rental cars. And within the sample mean miles driven is 325. Cool? Okay, so we're going to assume we know the population standard deviation for now. We're going to assume that it's, I lost it. We're going to assume that it's 60. So sigma x equals 60. And we want to know what the 95% confidence interval is. So our confidence level is 95%. So first, let's find our sampling distribution standard deviation, which is going to be the population standard deviation divided by the square root of our sample size. It's going to be 60 over the square root of 325. I'd love to give you guys the time to do that. Yeah, you can do it in a minute. 4.2426. That looks like I forgot the square root in my notes. That's fine. I'll fix that. Okay, once we know that, then we can draw the sampling distribution, our best guess for the sampling distribution of x bar. And as before, we know that this is going to be wrong, so I'm going to draw it in with a light color. Where am I? There we go. So this is our best guess for the sampling distribution of x bar. Looks something like this. We know that's likely to be wrong because the chances of being exactly right are so small. This is 325, and the standard deviation of x bar is 4.2426. Okay. So what we want to know is, if we are wrong, what are the outside limits, right? Let's put some bounds on this. Well, we're either weirdly high, in which case this is the true. Those are supposed to be the same shape, by the way. Close enough. That's the true sampling distribution, centered at mu1. Or we are weirdly low, in which case this is the true sampling distribution, centered at mu2. They all have the same curvature, right? Same dispersion, because we know this is correct, because we assumed we knew the stuff we needed for that. What we want to know is, what do we have to do to get this 325 to be just on the edge of normal? Okay. Now let's do this with mu1 first. What value would mu1 have to have for our sampling distribution, our sample that we pulled, to be weirdly high, but just on the edge? Well, we know that we want a 95% confidence interval. What that means is we want to know what value of mu will give us 325 right on the tip of the middle 95%. Okay, I'm going to run out of time in a minute, but I'm going to finish this up just to walk you through setting this up. Maybe I'll record another one. Okay, now because it's a normal distribution, it's symmetric, what that means is we can cut this down the middle. We know that the area over here is going to be 0.475. Okay, that's 9.95 divided by 2. 0.95 divided by 2 equals 0.475, which is essentially turning this into a question. We want to know what the value of mu is. We have x, we have sigma, we have some p, some area under a curve. We want to know what the value of mu is. So we can do this just like every other problem we've done so far. We relate it to the standard normal curve. I'm cutting across pages now. That's okay. It's going to give us some z value down here. Terrible curve, you get the idea. This is centered at 0, standard deviation of 1. We know that this area is 0.475. And what is the value of z? Well, z, if you look this up on your table, is going to give you a value of 1.96. Usually it won't be exact. But for now we know, but in this case it will, oddly. So, we know that z is equal to 1.96. And now we can go to the score formula to back out our value of mu. So, we want to know, let's see, we have our score function, looks like this. Z equals x bar minus mu x bar over sigma x bar. And we know that z is 1.96, which is equal to x bar, which was 325, minus mu1. Right, that's the hypothetical mean of the distribution in this case. All divided by, scroll up, we had 4.2426 is the value there. I have about a minute left. You want to multiply both sides by 4.2426. And then subtract 325 from both sides. That'll give you negative mu1. Or if you work it out, if you switch the signs, you can work it out that it's mu1 equals 325 minus 4.2426 times 1.96, which is going to give you 316.7. So 316.7 is our 316.7 roughly is our lower bound. That's mu1. It's the lowest reasonable at the 95% level of reasonability. That's the lowest value that our population mean could be. Okay, so that's part one. I'll solve for the upper bound, and then I'll walk through a few more things in just a minute. Thanks, guys. See you in a bit.